Hello, everyone. My name is Stephen Phillips. I'm an engineer and product specialist with T Equipment. We have a great webinar for you today. Will White, solar application specialist with Fluke, will be presenting commissioning and maintaining photovoltaic systems. Give a little background about Will. Will has been involved with the renewable energy industry since 2005, has experience in wind, power, solar, thermal, energy storage, and all scales of photovoltaics. Although he is primarily focused on residential and small commercial systems, including sales, design, and education for solar since that time. In 2002, he moved into the solar application specialist role at Fluke, where he supports their renewable energy testing equipment like IV trace cursors, electrical meters, and thermal imaging cameras. Before presenting, turning the presentation over to Will, we'll be waiting for any late joiners to the webinar here. I have a couple of slides about our company I want to show you. T Equipment is recently celebrated 21 years in business, and in that time we have become a very large stocking distributor. We really do take to heart the slogan, buy from people, not just the internet. And we have a qualified staff here to help you. Excuse me. As you can see from this slide, the national and international, we are an international distributor. We cover the needs of a wide variety of customer types. On the left side, you see on the right side, some of the products and instrument types that we carry in more than 500,000 products. As for our company has invested heavily in making the webinar a great resource. We are here to see the filter. Excuse me, I'm losing my voice today. Here you can see the filtering capability by specification to narrow your search faster on our website. We utilize an internal portal that better serve our customer service. We're also continuously enhancing our website and internal systems to provide better experience for our customers. It's time now to turn over the presentation to Will. If you have any questions, please ask them through the chat feature, and we'll be answering them at the end of the presentation.
Yeah, thanks, Stephen.
Okay, just give it a second here. Yeah.
Switch over my screen there. So as Stephen said, my name is Will White. I'm the solar application specialist at Fluke. I actually joined Fluke at the end of 2022, so I'm about a year and a half in. But I've been working in the solar industry since 2005, so coming up on 19 years this September. So in this presentation, I am going to talk about the tools and techniques for commissioning and maintaining PV systems. We're going to start off by reviewing category ratings, voltage ratings, and how that applies to the test tools that we're going to select for doing our testing in the solar industry. I'm going to talk about IEC 62446-1 briefly, which is a standard for testing grid-connected photovoltaic systems. Most of the presentation is going to talk about the tools that are used in testing solar from installation through commissioning and into the operations and maintenance stage of the system. The first thing we need to think about is transient voltage spikes. These are a large spike in voltage. They're very short duration, typically coming from the utility when we're thinking about solar installations. If you are working on a commercial system where you're in a commercial building like a manufacturer, you might get a voltage spike from something like a motor turning on and off. We can also get transient voltage spikes on the DC side from things like lightning strikes. They're unavoidable. They're invisible to regular test equipment. We can see transient voltage spikes with our higher end power quality analyzers, very short duration. The important thing is the last bullet on this slide, that if you have a piece of test equipment that is not properly rated, a transient voltage spike could overwhelm the tool. It could cause damage to the tool, and it may be a safety hazard to the person who happens to be holding the tool doing testing while the transient voltage spike happens. In order to deal with transient voltage ratings, transient voltage possibilities, we have category ratings. Category relates to the environment in which you are doing the test. They range from category 1 to category 4. The higher the category number, the closer you are to the source of a potential voltage spike, and the higher the danger from that voltage spike. According to this IEC standard, solar arrays were considered a Category 3 environment. We also do a lot of testing in Category 4 environments, which would be closer to the point of interconnection of our inverters, or if you're on a utility scale system between the inverter and the medium voltage transformer. Within a same category rating, as the voltage level of the tool goes up, the ability to withstand those transient voltage spikes increases as well. Once we know the category that we're working in, that's our environment, Category 3 on the array side, often Category 4 on the AC output side of the inverter, we need to know what voltage we're going to be operating at, or we're doing our testing at. And in solar, we have a wide range of voltage possibilities, everything from an individual module at 40 or 50 volts up to 1,500 volts on a utility scale system. We get AC systems that may be 208 or 240, 480, even 600 volts, or now 800 volts on the output of an inverter to a medium voltage transformer on a utility scale system. Whatever test tool we're going to select must have the category rating and voltage rating above whatever voltage we're going to be testing at. So if I'm in a residential system, I'll need a Category 3 600 volt tool for the DC side. Commercial and industrial rooftop systems can go up to 1,000 volts, and then our utility scale systems at 1,500 volts. The last bullet that's up on the slide now is also really important. Our test leads must be rated equal to our test meter. What can commonly happen is you have a meter like the 393 clamp meter, which is 1,500 volt rated Category 3. It has 1,500 volt rated Category 3 test leads, but if those leads should be damaged or misplaced, it would be common for someone to just grab whatever set of test leads they have laying around. And there's a pretty good chance that those are not going to be rated at the same level as those 1,500 volt test leads. So make sure that the rating of the leads matches the rating of the test equipment. Different voltages within the same different category levels make a difference on how large of a transient the tool can withstand. Here we've got a Category 3 1,000 volt tool is designed to withstand 8,000 volt transients, where a Category 2 1,000 volt tool can only withstand 6,000 volt transients. So even though they're both 1,000 volt rated, because that category rating changed, the ability to withstand those transients is different. I also like to point out that some meters are able to test at a certain voltage, like 1,500 volts or even 2,000 volts. But when you dig into the specifications, you find that they're rated at a much lower level, like Category 3 1,000 volts or even Category 3 600 volts. They're not designed or tested at that higher testing rating, so they're going to be less likely to withstand a transient voltage spike than a tool that is properly rated. All of the Fluke tools, if they are designed to measure a certain voltage, they are tested to that voltage level. You can find the category ratings right on the test tools. In this example, we have a multimeter with a Category 3 1,000 volt rated, Category 4 600 volt rated. Here's an example of our line of a couple of our clamp meters. The 325 clamp meter on the left is Category 3 600 volt rated. The 378 in the middle is Category 3 1,000 volt rated, and the 393 is Category 3 1,500 volt rated. These pictures are relatively to scale, so you can see as the voltage rating goes up, the size of the tool also goes up. And that's because there's more space internally in the tool to withstand those transient voltage spikes safely without damaging the tool or causing any problems with the safety problems to the technician who is using it. Now at Fluke, we design our tools to certain specifications, the category and voltage ratings for the tool, and then we have the tool sent off to a third-party listing agency who tests it and then lists the tool to that standard. So they look at the standard that we're designing the tool to and then actually test it to that standard and make sure it meets those requirements. Not all companies do that. Some will say that it's quote-unquote designed to a standard, but it's not actually tested by a third party, so we don't know if that will actually meet those requirements or not. When a tool is tested to a certain standard, the symbol of the testing agency will be stamped right in the case of the tool. We will typically use an organization like CSA or UL or TUV to do that type of testing. Not having that independent testing, you kind of never know what you're going to get if it hasn't been third-party tested. Now, IEC 62446-1 is the standard for testing grid-connected photovoltaic systems. This is a requirement in many European countries where they have to test and report to this standard in order to connect the system to the utility grid. Here in the US, it's not a legal requirement, but it is a good standard to use since we don't really have any other testing standards that are required by our jurisdictions that are approving these systems. In the standard, there are two main categories of tests. The category 1 test are safety tests. This includes checking the continuity of our equipment ground, so making sure our non-current carrying metal parts like module frames, racking, conduit, junction boxes, disconnects are all electrically connected together. We also test polarity, open circuit voltage, and short circuit current of our DC circuits. We'll make sure that our major components are functioning properly, so the disconnects work right, the circuit breakers are working, the inverter is operating properly. And finally, in this category, we'll do an insulation resistance test to ensure the conductors have not been compromised. The second class of tests are performance tests, and in this case, it's IV curve tracing, making sure that our modules and strings of modules are operating as we expect. And then this standard also requires all of these tests to be documented along with some other document requirements that will be transferred to the owner of the system. There's many stages in the life cycle of a solar installation, from the design and development stage, but we're really going to focus on installation and especially commissioning and operations and maintenance, because that's where most of our tests are done. And Fluke, of course, is a test and measurement manufacturer, so that's mostly what we're focused on. During the installation phase, a really good test to perform is insulation resistance testing. This is making sure that the insulation of the conductor has not been compromised during the installation process. We can also use insulation resistance testing to find ground faults. And essentially what it's doing is it's sending a high voltage, low current charge through the conductor. The conductor needs to be isolated from any other components and any electrical equipment. And then we're testing to see if there's any current leaking to ground. Fluke has a wide range of tools that can perform this test, from the handheld multimeter size insulation resistance testers like the 1587 and the 1507, one of which is pictured here on this slide. They will test up to 1,000 volts, so they can do 1,000 volt insulation resistance tests. The 1537 is a new product. It will test up to 2,500 volts in 100 volt increments from 250 volts to 2,500 volts. It's an excellent option for utility scale systems where you really want to do an insulation resistance test above 1,000 volts, but you don't really need the functionality of the higher end tools that will do 5,000 or 10,000 volt tests, which are significantly more expensive. So this is kind of a middle of the product line, a good voltage for utility scale systems. And finally, we have the SMFT 1000. This is a solar multifunction tool. It is capable of doing all of the tests required by this IEC standard, including insulation resistance testing. A unique feature of the SMFT 1000 is that it will do a regular point-to-point test from of your string of modules. It will test from positive to ground and negative to ground, give you the lowest insulation resistance value of the two. It'll also do a unique test where it will take the positive and negative conductors in the PV source circuit. It will short circuit them together internally in the tool and then measure the insulation resistance of that short circuit to ground. And what that does is it eliminates voltage potential between the positive and negative conductors and ground and gives you a little bit safer and more accurate test. Now, during the commissioning stage, we want to test voltage and polarity of our DC circuits of modules. Testing open circuit voltage, first we'll need to identify what the expected result is, the open circuit voltage of the module multiplied by the number of modules in the string. And then we can test voltage of our circuits. If we get voltage that's too high, it's often a result of too many modules being wired in the circuit. If we have voltage that's too low, we have too few modules. And usually these are paired together where someone put too many modules in one string and not enough in another string. Now, testing polarity is making sure that our positive conductors are all connected to the positives and our negatives are connected to negatives and nothing got accidentally switched. And it seems like a very simple test and maybe one that's easy to overlook, but at commissioning, before we have closed our fuse holders and turned the system on, we can relatively easily identify issues with reverse polarity and fix them fairly easily in many cases without any more difficult challenges to repair them. If we close our positive fuse holders, so in this picture here, and let me get my laser pointer going here. In this picture, we get a combiner box. All of our negative wires are coming in the top and going to this bus bar here. All the positives are coming into these fuse holders on the left and right side, and they're connected in parallel at the bus bar in the middle. If someone were to accidentally wire a positive and negative to the positive fuse holders, if the fuse holder is open, that's an open circuit. Their positive and negative are not connected together. As soon as I close those fuse holders, the positive and negative will be connected through the bus bar, and I'll have a short circuit current flowing through that circuit. If you were to open up one of those fuse holders under load like that, it's going to arc across the fuse holder, it's going to damage the fuse holder, it's going to be a safety hazard to the technician. So a situation that would have been very easy to repair prior to closing the fuses becomes much more challenging to deal with after we've closed the fuses. I want to point out the meter that's shown in this picture. This is a 393 clamp meter. This is 1,500 volt rated category 3. With most meters, both clamp meters and multimeters, when you get reverse polarity, you just get that little negative symbol. If you're like this technician in the picture, it's hot outside, it's sunny, you're sitting there just going down all these different circuits in this combiner box, it's very easy to miss that little negative symbol. Now, the 393 clamp meter, when it sees reverse polarity, you get the negative symbol, it says polarity on the screen, the entire screen lights up red, and it beeps at you. So it's basically impossible to miss a reverse polarity situation with that meter. Another meter that's a good option for doing these types of tests is the 283 multimeter. This is a new meter that will be coming out sometime in the second half of the year. It has the same reverse polarity feature that the 293 clamp meter has. The SMFT 1000 can also measure open circuit voltage, short circuit current, and can identify reverse polarity situations. Another test that's frequently done at commissioning is IV curve testing. This is a test conducted on our modules or strings of modules to see if there are any abnormalities with the production of the module. This is a test that can find problems that other tests like open circuit voltage or short circuit current testing would not be able to identify. Things like notches in the IV curve from a defective bypass diode. There's many other problems that we can see with an IV curve test. At commissioning, if we're doing a IV curve test of our entire system, we can create a historic record so we know everything was working properly when we started the system, and if there are any changes in the future, we can always refer back to this test data. At Fluke, we have 3 IV curve testers. The SMFT 1000 is capable of testing up to 1,000 volts and 20 amps. The 2 PVA products, the 1500 T2 and 1500 HE2, can both measure up to 1,500 volts and 30 amps. The big difference between these 3 models is how they handle high efficiency modules. That type of module, the cell has a high capacitance, and when the IV curve test starts, there's a large inrush current to the test tool. This can do a couple things. With some tools like the SMFT 1000, if the efficiency is above about 19%, they'll see that inrush current as an overload short circuit current, and they'll prevent the test from starting to prevent damage to the unit. Other tools like the PVA 1500 T2, when the efficiency exceeds 19%, their current rating goes from 30 amps down to 10 amps. The PVA 1500 HE2 is specifically designed for high efficiency modules. That's what the HE stands for. It will test up any module of any efficiency up to its full 30 amp current rating. So if you're working with high efficiency modules, which are typically above 19%, that HE model is the best option for you. And it's also, as far as I have seen, the only IV curve tracer on the market that is specifically designed for testing high efficiency modules. And we're the only company I've seen that even talks about how efficiency works with IV curve tracing. Another test that's done at commissioning is earth bond continuity testing. This is measuring between 2 points of metal equipment to make sure that they are electrically connected together. And I can really do this test between any metal parts in the system that are non-current carrying. So it could go from my module frame to the racking, from the module to the ground rod, between different sections of racking, referred to as tables in many cases. Any metal parts that are connected that should be electrically connected together, I can test for it. And in this test, I'm using ohms as my unit of measurement, and I'm looking for low ohms, which is low resistance. And these metal parts need to be bonded together because if they're not, and if there's a ground fault, it doesn't have an easy path to ground. And if someone were to touch that piece of metal part, they're going to become that easy path to ground, which is a safety hazard for the technician, and that's what causes electrical shocks and electrocution. Also, some overcurrent protection devices like circuit breakers need that return path to ground in order to operate properly. There's an IEC standard for this type of test that requires a 200 milliamp test, which is a current level that is much higher than what a standard multimeter is capable of doing when doing a continuity test. They're typically operating at 50 milliamps. The SMFT 1000 and the 1507 insulation resistance tester can both conduct this earth bonding continuity test at the 200 milliamps required by that IEC standard. A related test is ground resistance testing, and this is measuring to make sure that our ground rod or grounding electrode conductor or grounding electrode is properly connected to the actual physical earth. If there's not a good connection, we have the same problem we had in the last test where it becomes a safety hazard, overcurrent protection devices may not work properly. There are a couple of ways we can do this test. We can do a stakeless test, like the one that's seen pictured here. This is the 1630 meter. That one needs a parallel path to ground in order to do the test properly. The 1625-2 has several different options for conducting this test, including a staked test in a couple different versions. We often do performance testing during commissioning, and many times this is done using the data acquisition system included with either the inverter or the monitoring platform installed with the system. We're making sure that our actual production meets what we expected. We can also use this type of testing to calculate inverter efficiency. We're making sure everything's working right. In that commissioning, we're setting that baseline for the future to know that everything was working the way it should have been when we started the system up. At Fluke, we've got a couple tools that can measure power. The SMFT 1000 is the main one, and the screens that are pictured here are from that tool. That tool will measure power on the DC side, then it will measure power on the AC side, and it will calculate inverter efficiency between those two numbers. The limitation of that tool is that the clamp meter included with the tool is limited to 60 amps. So we would have to have an inverter with an input and output rating below 60 amps. And you need to ensure that you can get all the negative conductors into that clamp on the DC side. So if you had a combiner box like we saw a couple slides ago, that may be challenging with that quantity of circuits there, although that would probably exceed the 60 amp rating anyway. The Fluke 393 and upcoming 283 multimeter are also capable of measuring DC power. You would have to measure AC voltage and current separately and calculate AC power and then do the math between those to get that performance data if that's what you were looking for. Now in commissioning and in operations and maintenance, we can also do thermal imaging. Thermal imaging can be used on all kinds of equipment. We can use it on our electrical equipment, things like disconnects, combiner boxes, inverters, transformers. any type of electrical equipment that's got connections or electronics in it. We also see thermography of modules done very extensively in solar, especially aerial thermography, where they use a drone to fly over the array with a thermal camera. They take images, they analyze those images with a piece of software, and then they can identify areas that need further attention. When you're doing thermal imaging, you need to make sure that the system is under high load. So you want to have a high irradiance, so you're getting a lot of current flowing through the system. That's what's going to give you that temperature differential you can pick up on the thermal camera. Unlike many of our other tools, thermal imaging is, you can't just take a thermal camera out of the box and expect to get good results. You really need to get some training to make sure you know how to take good quality images and be able to identify what those images are telling you. Now, when doing thermal imaging, we're often looking for equipment that is hotter than it should be. And I should say in solar, we're not looking for a specific temperature. We're more looking for the temperature difference between similar pieces of equipment. We can also look for cooler equipment. That would indicate that there's lower or even no current flowing through that circuit. An example here in this picture, we've got a piece of equipment here. That circuit on the right is a much cooler temperature than the rest of the circuits. And that's because there is no circuit connected to that terminal. If this was a combiner box, that may indicate that there is a disconnect somewhere in that string of modules. At commissioning, we can use thermal imaging to create a baseline and a historic record so that we can review that later and see how things change over time. Although with thermal imaging, it's not always easy to compare things at different times because the ambient temperature might change, humidity might change. There are many things that affect those pictures. There are many tools we can use for thermal imaging. As I mentioned, drone-based thermal imaging is really common in large-scale solar arrays. Fluke has a wide range of thermal cameras from the small PTI 120 pocket camera, which is about the size of a cell phone, up to the mid-range and even high-end thermal cameras like the TI 480 Pro. As you move up in the product line, the resolution that the cameras are able to provide are much greater, and the higher the resolution is, the further away from the equipment you can be and still get good quality images. So you can be outside of the electrical hazard zone and still get a good thermal image. During operations and maintenance, a visual inspection is usually the first thing we do when we're doing any kind of maintenance or troubleshooting on the system. So walking around, see if we can find any issues. We're looking for things like burnt out connections between modules, wiring issues, damage to modules like shattered glass or damaged cells that are burnt out. Lots of different things we can see when we're walking around doing a visual inspection. It helps to have an inspector who is properly trained and knows what to look for. And the use of workflow checklists makes it easier for them to ensure that they don't miss anything as they're doing this visual inspection. That IEC standard we talked about has a large list of visual inspection items that need to be checked when we're doing our testing on our system. Those items are all included in a list in the SMFT 1000, which is what we see here in the middle of the screen. Each one of the items in that IEC standard are in there, and you can easily hit pass, fail, or not applicable, and save that data in the tool, and then export it to a computer later where you can create a very easy report to meet those IEC standards. Now, our inverters and transformers are going to need operations and maintenance as well. We can do DC and AC voltage and current testing. We can check things like fuse continuity. We can do thermal imaging. We can torque our terminals, make sure those haven't loosened over time. We can calculate inverter efficiency. And we can also do AC power quality measurements, like making sure the voltage and frequency are within specifications of the inverter. We can look for harmonics. With the higher end power quality meters, we can also check for transient voltage spikes. We can data log and see those spikes coming. Now, in this slide, you've got a technician using the SMFT 1000. And we just want to point out that this is a picture from Europe. They don't use conduit typically there. They use these cable trays. So it's very common to see wires coming out of the bottom of an inverter like we see here. Now, we do our maintenance on our inverters and our transformers because the manufacturer of those equipment has a list of things that need to be done on a regular basis. This is going to make sure that everything's working right. If we don't do the annual maintenance, we may void the warranty if there's any damage to the inverter or the transformer. Doing regular maintenance will prevent failures. It's going to make sure the system is operating to its maximum potential and get the best financial return we can get. Fluke has a whole suite of tools that can be used for this type of testing. We have multimeters and clamp meters for voltage and current testing. We don't have torque tools, but you can use torque tools for doing that test, doing that process. And then we have multifunction testers like the SMFT1000 that can do a series of tools. We also have power quality meters, and we even have networking tools to make sure our data communication is working properly. As I mentioned, our power quality meters can view harmonics. So if we're having problems with those, we can do some data logging. An interesting thing about a certain power quality meters is they're able to do load studies. So we can measure power and energy consumed by a load over time. Then we can take that information and use it to properly size an energy storage system for backup resiliency purposes. So a good tool for that if we're doing battery-based systems that are used for backup purposes. Now, our modules are going to need maintenance as well. Visual inspection is the best place to start with our modules. So walking around the array, looking for any kind of damage, burnt out connectors like we see in the picture here, any shattered glass, damaged cells, things like that. We can also do thermal imaging. We can also do thermal imaging of our modules. Aerial thermography is most common, but we can also use handheld thermal cameras to do spot checks of our modules. Any part of the module that is not operating will be at a higher temperature than the section of the module that is operating. And that's because when a cell's not operating or under load, the electrons are still being excited by the sun. They have nowhere to go, so they're dispersing some of their energy as heat, and that's what you're able to pick up on the thermal camera. But as I mentioned earlier, the system has to be under a pretty high level of load in order to get a good quality thermal image. Thermography, especially aerial thermography, is most commonly used to identify not necessarily the root cause of the issue, but where we're having problems and where we need to go to do further testing with other things like voltage polarity testing, IV curve testing, insulation resistance testing, things like that. With our modules, we can also test voltage and current. So we can do maximum power in open circuit voltage testing, looking for reduced voltage in that case. We can do current testing to see how strings are comparing to other strings. Most frequently with current testing in solar, we're looking for the absence of current. So I've shut my system down. I need to open up a fuse holder or a connection between modules which are not load break rated. So I want to verify there's no current in that circuit before I open up those pieces of equipment. If I should open one of those under load, it's going to arc between the terminals. It's going to cause damage to the terminals. It's going to be a hazard for the technician as well. I should also mention that we always use a non-contact current clamp to measure current in solar. If I am trying to measure current on my string of modules and I use a multimeter with the probe tips, as soon as I put the probe tips on the positive and negative, the meter is going to measure the current, assuming that it's below the current rating of the meter. But I've short-circuited that string through the multimeter. Once I remove the probe tips, that's under load and it's going to arc between the probe tips and the terminal that I'm measuring. It's going to cause damage and it's a safety hazard to the technician. So never measure current with the probe tips of a multimeter. Always use a non-contact current clamp. During visual inspection of our modules, again, having a trained person to do it is good. Having a checklist to make sure you don't miss anything. Thermal imaging we can do with a drone, we can do with handheld cameras. We have a suite of voltage multimeters and current clamps to measure both voltage and current. Make sure when you're selecting a test tool that it has the proper category and voltage rating for the environment and the voltage that you'll be testing at. So if you're doing testing on the DC side of the system, it's going to be a category 3 environment. you'll need a category 3 rated tool with a voltage rating higher than what you're testing at. If you're on the AC side of the system, depending on how it's interconnected to the either the electrical system in the building or the utility, it may be a category 3 or category 4 environment. Again, we need to make sure that we've got a rating, a voltage rating above the voltage at which we will be testing. Now, another common problem in the solar industry is ground fault. A ground fault is an unintentional connection between a current carrying conductor and a grounded metal part. There are two main types of ground faults: a solid ground fault, where it is a low resistant connection that is always present. Then the second type is an intermittent ground fault that comes and goes based on the conditions on site. And that could be they show up when it's wet out. It could be that it's getting pinched by a tracker at a certain time of day, or maybe when it's windy, the wire bangs into the metal array, the metal racking, and becomes grounded. Pinched wires, say between a module frame and a piece of racking, are very common causes of ground faults. We can also damage the wires when we're pulling them through the conduit. If we have insulation that's not proper, or I should say, if we have wire that's not properly managed and the insulation is rubbing up against a piece of racking or maybe the corner of the module frame, over time, that insulation is going to wear away and is going to cause a ground fault. Now, we can do a couple things to find ground faults. Voltage testing on our string of PV modules is a way to find a ground fault. We can test between the positive and the negative and get our open circuit voltage of the circuit. Then we can test from positive to ground and negative to ground. And there should be zero voltage if the system is working right, assuming that it's a modern inverter and that when the inverter is off, there is no connection between the DC side and the ground. Sometimes you'll see a voltage when you first start testing, and that will bleed off pretty quickly. That's a ghost voltage, and it's not actual voltage of the string. You can also use insulation resistance testing to find ground faults. It's very good on circuits that are de-energized when you turn the system off, like our PV output circuit between the combiner box and the inverter, or the inverter output circuit between the inverter and our point of interconnection. You shut the system off, and those should be de-energized. Oftentimes, insulation resistance testing will tell us which circuit has the problem. It's not necessarily going to tell you where the problem is. And sometimes we'll see strings or tests that are still passing according to the IEC standard, which requires about 1 mega ohm to pass that insulation resistance test, but the value is less than everything else. So an example of that is I was doing some insulation resistance testing on a low slope commercial roof. All of the strings were exceeding the maximum resistance value of my meter, which was 2 gigaohms, except for one string. It was measuring at about 156 mega ohms, which is still way beyond the minimum value for the IEC standard, but it was different than the other strings in that system, which were all basically the same. When I tracked down that string, I found that a module interconnection between the two modules was laying in a puddle on the roof. So even though it wasn't a full ground fault, we were still losing some resistance to ground there. As soon as I lifted that out of the puddle, properly affixed it to the racking and let it dry off for a bit, the insulation resistance of that string also exceeded the 2 gigaohm limit of my meter, so it matched all the other circuits in that system. Ground faults can be a safety hazard. We have current flowing to a non-current carrying metal part that may be energized, especially if we have a poor equipment grounding system. If there's no easy path for that current to ground, if someone touches that metal part, they may become the path to ground, which causes a shock and possible electrocution. It's a fire hazard if there's arcing there, that would be an arc fault as well as a ground fault. That arcing may cause sparks that might lead to things like grass fires. It's also reducing system production. If I have current that's flowing to the ground, it's not flowing to my inverter where it should be going, where it's utilized by our loads. I can use any clamp meter or multimeter or insulation resistance tester with the proper category and voltage rating for the system that I'm working on. So let's take an example of how to use voltage testing to identify the location of a ground fault in a string of solar modules. So here I've got my multimeter. I have a string of modules. This is 16 modules, approximately 53 volts per module. If I test from negative to positive, I should get the open circuit voltage of the string of modules, which is simply the open circuit voltage of an individual module multiplied by the quantity. In this case, I get 861 volts. If I measure from the ground to the positive, I should get 0 volts, but in this case, I get around 645 volts. If I measure from the negative to the ground, I should also get 0 volts, but in this case, I got around 215. I'm going to record all these results and do some analysis. So when I look at my results, from my positive to the negative, I get around 861 volts. Divide that by 53 volts in the module, and I get 16 modules. And that's never going to be exact. I'm going to get some variations there due to environmental conditions in the system design and how it's put together, but it's getting pretty close to 16. When I measure my 645 volts positive to ground by 53, I get approximately 12 modules. When I measure the 215 by 53, I get approximately 4 modules. Now, what this tells me is that there's a ground fault 12 modules from the positive to where the ground fault is, and 4 modules from where the negative is to the ground fault. So if I'm counting from my negative side, this means the ground fault is between module 4 and module 5 of the string. With that information, I can get the string layout. I can go out into the array, figure out where these modules are, and try to do a visual inspection to see where the problem is, and then repair that ground fault. Another quick example, positive to negative, same as the last 16 modules. Positive to ground, I got full string voltage, 861 volts. That's 16 modules worth of voltage. Negative to ground was 0, which is what I expected. This means that from the positive side, there are 16 modules between the positive side and the ground fault. And on the negative side, there are 0 modules between the negative and the ground fault. This indicates that the ground fault is on the negative home run conductor. Now, this type of situation is very common and can be very easy to miss because the readings that you get from positive and negative to ground are all numbers you expect. You expect to see 861 volts between the positive and the negative, not between positive and ground, but sometimes your brain forgets what you're testing and you miss that. And the 0 for negative to ground is what I want. So be aware of these. These can be harder to track down because the home run may be significantly longer, and I might be a conduit. I might have to go through and do some further analysis there. Another problem we get with solar installations are arc faults. An arc fault is a resistance connection. There are 2 types of arc faults. There's a series arc fault where I have high resistance in a circuit where I want low resistance. An example could be the module interconnection we see here in the picture. We've got a positive and negative connector between 2 modules. Something is wrong with that connector. Either it wasn't plugged in all the way, or it was damaged, or they got some kind of corrosion or mud inside the connector, or they made a connector in the field and they did a bad job making that connector up. And something in that connection is arcing and causing increased resistance. I don't want that. I want low resistance. The second arc fault is a parallel arc fault. And this is the opposite. It's where I have low resistance when I want high resistance. And an example here would be a DC positive making connection to a DC negative. They should be separated, but for some reason they rub together, and now the positive and negative are making a connection. In both of these situations, the electricity is arcing between the 2 sides, either between the high resistance connection or between the low resistance connection between 2 conductors. Finding all arc faults is notoriously hard. I can do visual inspection looking for burn damage. In the example we see here, the picture on the left, I believe that this started as a series arc fault in this connector. You can see there's a little bit of a gap between the positive and negative side of the connectors. And that should not be there. They should be butted right up against each other. I think that this was arcing in this series connector and started to melt it. And then it looks like that connector was really close to this wire, and it made a parallel connection between the connector here and this wire there. So I think this is both a parallel and series arc fault. Thermal cameras can be used to find arc faults because if it's faulting pretty badly, it's arcing there and that's releasing heat. So I'm not necessarily looking for a specific number, but I'm looking to see how that connection compares to other connections in the system under the same environmental conditions. So I can't go out one day, get some pictures, go back a different day where the environmental conditions are different and expect to get good results. Inverters have arc fault protection built in, all modern inverters at least. If the inverter throws a fault code, what you can do is a troubleshooting process where you eliminate sections of the array, turn the inverter back on, see if the fault code comes back. If it doesn't, you know the fault is in that section of the array that you isolated. If it does come back, you know it's not that section, so you can reconnect it, shut the inverter off, disconnect a separate section of the array, and turn the inverter back on and see if the fault code goes away. By doing that, you can kind of do a process of elimination to figure out where the fault is. Arc faults are a big safety risk. They're an electrical hazard, they're a fire hazard. Both series and arc faults are eventually going to burn themselves out. In the picture here, we had a module interconnection. One of the sides was not fully mated with the other side, so there was a high resistance connection there. Eventually that burned the insulating plastic on the outside of the connector away, which caused a fairly significant fire on this roof. We can use thermal cameras in troubleshooting workflows to potentially identify arc faults. I will say that arc faults are one of the most difficult problems to find in a solar array. Doing all this testing and gathering all this data, I need to do something with it. We want data that's easy to record, easy to catalog, that I can get back when I need it, and that's accurate. Having workflows makes it a lot easier to ensure that technicians are doing the same thing every time and getting the same results, especially between different sites and different technicians, especially when we have newer technicians. Our test equipment needs to be calibrated on a fairly regular basis, and most Fluke tools recommend an annual calibration, and so having it sent out every year to be calibrated. Sometimes when you're doing third-party operations and maintenance, especially if you're doing testing, if an asset is going to be sold, they'll want to make sure that you have a certificate of calibration for your test tools before you go out and do the testing so that they know that the test results are accurate. Okay, to summarize, we need to make sure that whatever tool we're selecting to do our testing has the proper category rating, category 3 on the DC side, category 3 or category 4 on the AC side, and that the voltage rating is above whatever voltage we're going to be testing at. There are lots of different tests done in the solar industry. Fluke makes a tool for every test that's done in solar. So making sure that you have the correct tool makes it easier and makes it a lot safer when you're doing the testing. We need to calibrate our test tools to making sure that they are taking accurate measurements. And finally, we need to make sure that we're wearing the proper personal protective equipment when we're doing our testing. In the solar industry, we are often working on systems that are energized, like the technician in the picture here. They're wearing the proper equipment. They've got fire-resistant clothing on. They've got electrically insulated gloves. They've got their arc flash face shield and balaclava. The only criticism I have for this picture is that the technician is kneeling. That makes it a much easier path to ground as opposed to if he was standing and wearing his boots with his rubber soles there. But other than that, he's got all the proper equipment on, which is really important when we're doing testing of lives.